8, Stokes' theorem. I'm going to go over a proof of how this works, what Stokes' theorem is and why it works, go through the math of why it works for one particular case of Stokes' theorem. But I'm also going to post a video from Khan Academy that gives you kind of a more tangible, like a more intuitive understanding of the proof, which I think is very useful. So what Stokes' theorem says is the line integral of a vector field f dot dr, remember this is for a curve, okay, and this is going to always be a closed curve, okay, is equal to the double integral of the curl of f dotted with your surface. Okay, so this is like the flux, but it's not just flux. Another way to think of this thing, or when we calculate it, it's the curl of f dotted with your normal over your surface. These two things mean exactly the same thing. When you see this in your book, this is going to be a bold ds because you're finding the flux of this thing through the surface, which really means, oops, forgot the L. You're taking the component of the curl that's in the direction of the normal and evaluating that over your surface. Okay. This thing over here, another way to calculate this, remember how we calculate this, this is really f of r of t dotted with r prime of t dt, or another way to see that is your m dx plus your n dy plus your p dz, and that's equal to this double integral of the curl of f dotted with your normal over your surface. Okay, and just to draw a picture, I know that you can look at a video and see what this is doing. But when you've got some kind of a surface, so you've got this curve going through space, okay, and it has to be a closed curve, and there's some kind of a surface here. Now, this applies to any curve, any surface. If you're going to calculate it this way over surface, any surface that has this boundary curve. So it can simply be this surface here. Okay. It could also be, you might have some kind of almost like a paraboloid that goes up and opens down and has the same boundary surface. So that's the convenience and the flexibility of this theorem, is you can think about this theorem applied to different surfaces as long as they have the same boundary curve. Okay, now we're going to take this and we're going to basically project onto the xy plane this surface, okay, and this we're going to call D, it's the domain. So this is this curve here, we're going to call this C, projected onto the xy plane, and it would give you this domain down here, and that's going to come into play in a little bit. Okay. Now, what we're going to do, first what I'm going to do is I'm going to calculate, I'm going to start with the right side of the equation. We're going to calculate this and come up with an expression, and then what I'm going to do is go to this side, and I'm going to come up with an expression. I'm going to show that those expressions are equal to prove the theorem. Okay? So, we're going to start with the curl of f, the double integral of the curl of f dotted with your normal over your surface. Now, let's find the curl of f. Remember what f is. F is going to be the vector field made up of m, n, and p. Remember, m, n, and p are all functions of x, y, and z. And if we want to find the curl of f, we do the I, the j, the k, the d dx, the d dy, the d dz, and then m, n, p, and then it comes out to be dp dy, and I'm going to write it this way. It's the y partial derivative of p, so py minus the z partial of n and z. And then the j, we've got the x partial of p minus the z partial of m, but it's the j, so I'm going to switch that order. So the z partial of m minus the x partial of p, and then in the k direction, I've got the x partial of n minus the y partial of m. Okay, so that's the curl. The curl of f equals this thing. Okay, now I also want to refresh when we find flux, the double integral of f dotted with n ds. Remember what we're actually doing here when we calculate this. You would have the double integral of f of r of uv. You've parameterize your surface with respect to u and v from any two parameters. And then we dot that with Ru cross Rv, du dv. Now, there was another way you could do this. If your z value was a function of x and y, this simplified a little bit differently. Okay, so what you had here was you had your f of r of uv, or in this case, it's going to be r of xy, dotted with, and this ru cross rv, remember what that came out to? It came out to the opposite of dz dx, opposite of dz dy, and then 1. Okay, and that was a vector dotted times dx dy. And what this came out to was opposite of m, okay, because this f was really mnp, mnp. So opposite m dz dx minus n dz dy plus p, and that's over your dA, the dx dy. Okay. So the reason I remind you of this, that's flux when you're taking the flux of f through a surface. Well, we're not taking the flux of x through a surface. We're taking the flux of the curl of f through that surface. And the curl of f is this thing, okay? So really, if we're going to apply this theorem here, our m is really just this entire thing. The n is this entire thing. And the p is this entire thing, okay? So we're actually proving this theorem only for the case when your z value is a function of x and y. Okay, so we're proving it for this, which is many of the cases. You can see this function here the way I've drawn it. Your z is a function of x and y. So we're just proving it for this one case for now. Okay. So I'm going to apply this theorem down here. I've got the opposite of m. Well, our m is really this thing, so the opposite of py minus nz dz dx minus n, which is this thing, mz minus px dz dy, and then I've got plus p, so plus the p, which is this thing, and x minus my. Okay, and that entire thing is going to be over your area, dx dy. I'm going to simplify that a little bit, and that should have been a double integral there, right? Okay, so double integral of, I've got opposite dp dy dz dx plus dn dz dz dx. I've got minus dm dz dz dy, then plus dp dx dz dy, and then I've got plus dm dx minus dm dy. This entire thing is over your dA, the dx dy. Okay, so this is what we've got for the right side of the equation. If we look here, this comes down to this. So what I'm going to do next is I'm going to evaluate this side of the equation and show that we get an equivalent expression. Okay, so I'm going to go to another page, and we're going to show the other side of the equation. Okay, so what I'm going to now show is this part over here. So the integral of f dotted with dr, okay, over this curve, and I'm going to show that that's going to be equal. Okay, so the way that we calculate this thing is you've got m dx plus n dy plus p dz, okay, going around your curve. Now, I'm going to just rewrite this as an equivalent expression, m dx dt plus n dy dt plus P dz dt, and then we've got a dt out here. Okay, and there's a reason I'm going to do that. Because if z is a function of x and y, and x and y are both functions of t, we need to apply a chain rule. Okay, so we've got the integral of m dx dt plus n dy dt plus p, and the dz dt is really equal to dz dx dt plus dz dy dt. So dz dx dt plus dz dy dt. This is all over dt. Okay, now I'm going to take these dt's and I'm going to cancel them. Actually, yeah, I'm going to cancel this dt with this one and this one and this one and this one. So I really just have m dx plus n dy plus p dz dx plus p dz dy dy. Okay. Now I want to put all of the dx's together. So this one and this one I'm going to put together. So I've got m plus p dz dx times your dx plus, and I want to put the dy's together. So I've got n plus p dz dy dy. Okay. So at this step here, I'm now, notice everything now is in terms of x's and y's. Even though I've got a dz dx, that's going to be in terms of x's and y's. And that's going to be in terms of x's and y's. So this looks a lot like Green's theorem. So right now I'm going to apply Green's theorem. Remember what Green's theorem says, is the integral of f dotted with dr equals the double integral of the n dx minus the m dy, and that's all over your dA. Okay, so that's what Green's theorem is. So basically what we have here is this thing, which is your f, so this is m dx plus n dy, that's another way of writing this, is equal to the double integral of the n dx minus dm dy over your area. So what I have here on this side, here's something with the dx plus something with the dy. So this thing I'm now treating as my m. This thing I'm treating as my n. So when I use Green's theorem and turn this into this thing becomes the double integral of, now I need the x derivative of this minus the y derivative of this. So the d dx of n plus p dz dy minus the y derivative of this. So the d dy of m plus p dz dx. Okay, and that entire thing is over your area. Okay. Now, the next thing we're going to do, actually, I'm going to go on, I'm going to start simplifying this, because remember what our goal here is. So this came from this side of the equation. We already showed that this side of the equation became this. So now all we have to do is show that this is equal to this. Okay? So that seems easy, but it's a little bit more complicated than it seems, and I'm going to do that in the next video.